Up to now, we have discussed very simple linear models. We have discussed what is linear regression, where we always use some linear function to predict the output from your input. And also we discussed some logistic regression and LDA. These algorithms generate some linear discriminant functions. And at the time, the number of parameters was also very small. So from the simple model, you can expect very tiny generalization gaps. So very minor overfitting issue will be there because of the simplicity of your model. So this is good because we don't need to worry about the overfitting. But in reality, the ground truth is never linear. The ground truth not linear, but some complicated function in some cases. And if you use simple linear function to predict such a very complicated function, you have to consider some bias error. So for instance, if your ground truth function is this, but if you train your model using very simple linear regression, from the difference between the ground truth and your simple model, naturally your model will have some high residual sum of square error, and this is called bias error. So we have to consider nonlinear approximation or nonlinear predictions. And this week we will discuss how to design very nice nonlinear approximations. Okay, so there are many possible nonlinear models and a lot of models actually there. So among them, I want to introduce two very simple extensions of linear regression model and linear model for classification task as well. The first one is polynomial extension. So previously we just used beta 0 plus beta 1x to predict your output, and you just simply use this logic function for your logistic regression. But as I said, the ground truth never linear, and this algorithm naturally have a huge bias error. So instead of using this simple linear function, we can use this polynomial function. Square or cubic function, or even more beta d xt with degree d polynomial. The logistic regression case as well, you can extend the simple logic function to degree d polynomial. And all the remaining thing will be the same. How can we find the parameter beta 0 to beta d? How can we find? For the regression task, we just need to define loss function using RSS and then find parameters that minimize the RSS. For the classification task, we define likelihood function for your objective function and then find beta 0 to beta d, then maximize the likelihood function. That's it. Okay. And since we have more degree of freedom to predict your output y, we can expect much better performance. For training error, we can expect the better training error, as you increase the number of parameters, since new model always include the previous model. Essentially, when you set beta d equal to 0, then this model is just degree d minus 1 case. So we just simply expanding our model set. So as you increase the number of parameters, we can expect always decrease the training error. Always. So we can expect this kind of training error curve as the degree d increase. But the problem is, what we want to do is not optimizing or not minimizing the training error, but we want to minimize the test error. And the test error can have this U-shaped curve because of overfitting. Right? So it is very important to find the nice D that optimize the test error. Okay, and how can we find such nice D? Of course, cross-validation is one very nice approach. Okay, simply split your entire data set into two different parts, training and test, and just training with training data, and then validate your trained model using test data. Okay. The second extension is piecewise function. For instance, step function. So when you have many data points here, and if you think this is not good shape for linear regression model, you can employ the degree d polynomial, but also you can introduce some artificial intervals for your input domain, and then define different function for each domain. And most simple case is step function, so define a different constant here to predict your output y. Okay, and you can do better than linear regression in this case. And as you increase the number of range and number of partitions, then you can expect better training accuracy because you have more degree of freedom. Each interval introduces one more parameters here, essentially, right? And you can use polynomial function for each interval as well. You can use some linear regression for each interval, or you can use some cubic regression for each interval as well. Okay, right. So this is called piecewise polynomial regression. All right, it's good. This is better than just step function. And as you split more range or more intervals, you can make more accurate prediction for your training dataset. Right? Since you have more parameters as you increase the number of intervals. But when you look at the curve, when you look at the function, this is very unnatural. Why? Because of this discontinuity of your function. This discontinuity is very ugly. Right? Discontinuity is very ugly, and I don't want this. And many statisticians, many machine learning researchers also hate this discontinuity because this is very unnatural So many people believe this discontinuity will increase the generalization gap. Generalization gap means the difference between test error and training error. So even if you can decrease the training error from the more flexibility and more degree of freedom for your model by introducing more intervals, but because of this very artificial function shape, very ugly function shape, comes from the discontinuity, which can make a very high generalization gap and maybe the test error pretty bad. Okay. So spline comes up. We now discuss what is spline and why spline looks very natural in the next video.